This is active filter design lecture 27. In the last class, we were looking at how one might be able to implement what we called a fully differential transconductor, where the idea is to be able to generate two currents which are plus Gm times Vd and minus Gm times Vd, where Vd is the differential component of a set of voltages, right? And the tail current was denoted by 2 I naught, and we found that it is just not possible to have two independent current sources as the loads for these transistors, right? And these transistors which are acting as current sources must indeed be controlled by or dependent on I naught in some fashion, right? Always being such that the sum of these two currents must be equal to I naught, okay? And to figure that out, I mean to keep these currents equal to 2 I naught when added together, what we did was, instead of monitoring the currents and then comparing them to 2 I naught, we said it's simply easier to monitor the common mode voltage at the outputs using some kind of common mode detector, okay? And the output of the common mode detector will be what? VOP plus VOM by 2. We compare this to the desired reference, which we will now call the common mode reference, right? Because this reference voltage is what sets the output common mode voltage when Vd is 0. And this completes the negative feedback loop, okay? So, the portion shown in red is what is called the common mode feedback network, right? And as you can see, there is a loop, a feedback loop going like this, but this loop is only active for common mode signals if VOP and VOM move in the same direction, then this loop works. If VOP and VOM move from a common point in the opposite directions, then the detected common mode will not change, right? In other words, for a purely differential output, the detected common mode voltage will not change, which means that this voltage at the output of this amplifier here will not change, which means that there is no feedback action in response to the differential voltage, correct? Now, the next thing we need to figure out is how one might implement this using transistors, how one might implement this, okay? And what else do you think might be important? Okay, fine, we implement how to implement this, and what else? Whenever you have a feedback loop, what do we need to worry about? We need to worry about the stability of the feedback, correct? Okay, so let's start from this character. What is the easiest thing you can think of which will take two voltages and generate their average? A resistive divider, good enough. Okay. So, in other words, these two resistors are doing the job of computing the average of VOP and VOM. All right. So, can you now comment on the suitability of or the good and the bad points of this common mode detector? What is good about it? Pardon? It's simple to implement. More importantly, please note that if the resistors are linear, which is a very good assumption on a chip, okay. All right. Then what do you think this potential is going to be? It's going to be the common mode without any error whatsoever. Okay. If the resistors were non-linear, that need not be true. Okay. So let me put down these observations. So if you have a resistive common mode detector, right? What is this? This is very linear in the sense that please note that the job of the common mode detector is to faithfully reproduce the common mode voltage only without any, I mean, an ideal common mode detector will only give you the common mode, right? So what do you think a non-ideal common mode detector will do? Some differential mode also will appear at the output, right? In which case the common mode feedback loop starts to respond to that differential mode quantity, which ideally it I mean it shouldn't happen, because we are interested in making the common mode loop work only for common mode signals. You understand? So the one of the good points of this resistive common mode detector is that the output, if the resistors are linear, then the output or the detected common mode voltage is devoid of any differential mode component. What do you think will happen if the two resistors are not matched? I mean, it's not a far-fetched assumption to assume that the two of them will be slightly different, correct? Then what do you think will happen? There will be a small differential mode quantity also, okay. All right. Hopefully the matching between these resistors on a chip is so good that the differential mode quantity is very, very small. Is this clear? Okay. What do you think are the bad points of what do you think might be a disadvantage of this RCM using resistors? Pardon? Current in which loop? There are many loops. Huh? Yeah. So basically, as far as the differential mode equivalent is concerned, how does this look like? Ideally, we'd like to see a transconductor which generates GMVD this way, and this is VCM plus VD, this is VCM minus VD. All right. Now, what are these two RCMs doing? In the differential mode equivalent, how do they appear? From output to ground, okay, or you can draw them in this way. Please note that if the two RCMs are equal, then this node potential, right, does not change when the differential mode voltage changes, correct? Because if this goes up by some amount, this goes down by exactly the same amount, the middle point potential does not change, which means that it is equivalent to small signal ground. Okay, it's exactly the same fashion why this does not change for purely differential signals, right? So since this is small signal ground, okay, now we see that in the differential mode equivalent you have two resistors like this, And in other words, what is now happening to the differential mode circuit? Ideally, a voltage controlled current source should have infinite output impedance. Now, you added these two resistors to detect the common mode, but they are screwing up the differential mode performance by reducing the output impedance. What implication does this have in the filter? What will happen to the quality factor? It will reduce. Okay, this is exactly the equivalent to saying the effect of finite transconductor gain on the filter performance. We went through all this before. Okay. All right. So, unfortunately, while the resistive common mode detector is very good as far as linearity is concerned, it's bad because it loads the okay. All right. So, now that we have encountered a problem with this, please note that oh, all right. So, all right. So, what do you think this is? So, the problem is that these two guys are loading the differential half. So, what do you think we can do to fix the problem? Okay, one straightforward solution is I will make RCM larger and larger and larger, right? Engineering solution. Okay, so what are the problems with the solution? Okay, well, there are several problems. One, of course, making a larger resistor means that physically it's larger. Okay, it turns out also that whenever you make a resistance, you also pick up. I mean, you can think of this as the chip. Okay, so the resistor is made in some layer, on top of the chip. So if you think of a strip of resistive material lying on top, there's always a capacitance between this point and the resistor and ground. So the larger you make the resistor, the more the parasitic is going to pick up. So parasitics of the resistor are a problem. What else? Noise is not important because as you make the resistor larger and larger, in fact, the noise contribution comes down, isn't it? Okay. All right. What else? Okay. So though you have not seen it yet, if now you make these resistors larger and larger, there is always bound to be some parasitic capacitance at every node. Okay. So which means that if the common mode changes in a step like fashion, correct, what do you think will happen to the detected common mode? It will not do so immediately, it will do something like that, which is equivalent to saying there is a extra pole in the feedback loop. If you have an extra pole in the loop gain function, what do you think will happen? Phase margin will reduce, okay, so thereby compromising the stability of the, okay. So these are all the problems with using large RCM. Is that clear? Okay. So, can somebody suggest another fix? Simpler. What do you think you can do? I mean, why is there a problem in the differential part? Pardon? No, the problem with having resistors was that in the differential part, current flows in this fashion, correct? And thereby this current will steal some of the current that the transconductor is putting out. Ideally, why is the resistor a problem here? Because the transconductor is putting out GMVD, some current has to flow through those common mode detecting resistors. So, some part of that GMVD is getting lost. I mean, that's in simplistic terms, that's the problem. So, how do you fix the problem? Come on, people. See, please don't jump into circuits right away. First, think about, in principle, what would you like to do, right? Then you can always replace those, whatever building blocks you need with transistor realization. Pardon? Yeah, you have to stop that current. Okay. So, one way of stopping the current is cutting off these leads here. What is the problem with that? Is this so difficult or what? Somebody said, okay, the problem is the current. Let's stop the current. So I will say, okay, I will cut these wires. There is no feedback. So what is the? So not only do you need to stop the current, you also need to. Yes. Shravan Siddharth, what do you think we should do? We should not allow. So what can you call a contraption which senses the voltage V out is equal to V in, but I in equal to 0? A voltage controlled voltage source. So in the simplest case, a voltage controlled voltage source of gain 1. Correct? All right. So if you want to build these voltage controlled voltage sources using transistors, what is the simplest transistor based voltage controlled voltage source that you know? The source follower, the common drain amplifier. So what we will do is replace this detector with something based on a I've just chosen a current I naught. There is no, in fact, there is no holy grail asking you to choose this to be I naught. I just chose it to be I naught because it avoids me having another symbol. Okay. So this is the voltage controlled voltage source, incremental voltage controlled voltage source. I can do the same thing this is I naught. All right. So what would I need to do now? Connect resistance between which 2 points? Source to Okay. Now let's see what problems this brings. All right. So now this is RCM. Okay. What is the okay? If VOM was equal to VOP, what will be the detected common mode voltage? Okay. What is this quiescent voltage? What is this quiescent voltage? Yes, Chinnadurai, what is the quiescent voltage at the source? Assume VOP and VOM are the same. What is the quiescent voltage at the source of that common drain amplifier? Yes. We know the current I naught, yes. Dinesh Jayaraman. Yes, Yogesh. Yes. Yeah, okay. So let's assume that the overdrive is delta V. Okay. Then what is the source voltage now? VOP. What is the gate source voltage? The source voltage is the gate voltage minus the gate source voltage, guys. What is the gate source voltage? What is the gate source voltage? Vt plus delta V. So what must be the source potential? VOP minus Vt minus delta V. Right? Okay. Similarly, what is this source potential? If VOPM and VOP are the same, in other words, there is no differential output, then uh, the quiescent voltage at both the sources will be the same, and it will be equal to VOP minus Vt minus delta V. So what will be the detected common mode voltage? VOP. If VOP is the same as VOM, then both the sources are the same voltage. So when you join those two voltages together, nodes together, you get VOP minus Vt minus delta V. Okay. All right. Is this clear? Okay. So let's see. So what will be the output common mode voltage here? If the input differential voltage is 0, then the common mode feedback loop will force the output common mode voltage to be some reference value. And what is that value now? Why? So the common mode feedback loop is going to force the two voltages at the input of that common mode error amplifier. Okay. Please note that this difference, the difference between the positive and negative terminals of that op-amp, is nothing but the common mode error, which is the difference between the actual common mode, or difference between the detected common mode and the common mode reference, right? So this amplifier is often also called the error amplifier, correct? So if the negative feedback loop is functioning properly, then the positive and negative terminals of this error amplifier must have the same potential, which means that the VCM of the output nodes of the transconductor minus Vt minus delta V will be what does this represent? This is the detected common mode. Correct? And this must be equal to VCM ref. So, what do you do now? So, what is the common mode output actually? Is VCM ref plus VT plus delta V. Correct? Okay. And so, why do you think there is an error? I mean, originally we had intended the output common mode voltage to be VCM ref, isn't it? Now it is VCM ref plus something plus something. So, why do you think there is an error intuitively? It comes out of the math all right, but where is the error coming from? I mean, the culprit is the common mode detector. It's supposed to give you V common mode, it sends the common mode properly, but it is adding its own masala to the sensed common mode and giving you in fact the output common mode minus some fixed quantity, right. The poor error amplifier only knows that it has to make these two the same, correct. So, that is only possible when the output common mode is more by Vt plus delta. Does it make sense? All right. Now, how will you fix this problem? So, we realize that if you want to fix this, what you should do is replace, instead of having VCM ref, if the reference to the common mode loop was VCM ref minus Vt minus delta V, then the output would be VCM ref. Okay, so how do you generate VCM ref minus Vt minus delta V? You can copy and paste 1/2 of the detector. VCM ref okay. So, this voltage now becomes VCM ref minus Vt minus delta V, correct, and therefore, the common mode output of these two nodes will be VCM. Is this clear? Okay. All right. So, this again, as I said, there are a million ways of detecting the common mode. You will see more of such detectors in your assignments, but this should give you an idea of what is happening. Now, let us understand what happens when the detector is excited with differential input signals. In other words, when this goes up by, so now the way we have done it under 0 input differential conditions, the voltage here will be how much? When Vd is 0, what is the quiescent voltage at that node? VCM ref. What about this guy? Also VCM ref. In response to some differential input voltage, let us say this goes up by V1, what will happen to the other arm? Should go down by V1. So, what will happen to this voltage? Under what condition? So, what will be the total voltage at that node? The quiescent voltage, which was VCM ref minus delta V minus Vt, plus small v1, and why is it, under what conditions is will it be plus v1? See, for differential mode signals, what is the differential mode equivalent circuit of the common mode? Please note that this is the common mode detector. I am just drawing that separately now for aid in understanding. This is I0, this is RCM, VDD, this is VCM plus VD, this is VCM minus VD. So, what is this? This voltage absolute potential will be VCM minus VT minus delta V. Okay. But what I am interested in finding out is the incremental voltage here. The quiescent voltage there is VCM minus VT minus delta V, right? Now, if VD is applied at the gate, what do you think will happen to the voltage at that node? It will go up, correct? By how much will it go up? Very good. It will go up by VD times GMR by 1 plus GMRCM, correct? So, under what conditions will, so this will be VD only when GM times RCM is much larger than 1. Okay. Similarly, this will be minus VD times GM times RCM divided by 1 plus GM times RCM. Okay. So, incrementally, what about this node incrementally? This will incrementally be 0. So, in other words, this voltage will be VCM minus VT minus delta V irrespective of small changes in VD, correct? Whereas, if VD was 0, if VCM changes by some amount, how much will the common mode detector output change by? In other words, what is the incremental gain of the common mode detector for common mode inputs? What is the common mode equivalent circuit? In other words, if this was changed to VCM plus small VCM on both sides, what will be the change in the detected common mode voltage? Same what? Which same thing? Why? No, that. Okay. Okay, how will you figure it out? Animesh, how will you figure it out? No. Please don't ask. Don't. I asked you how you will figure it out. Don't give me the answer. No, both the voltages are the same. Correct? So, you can use simply half circuit analysis. What is the current? Both sides are the same. So, what is the current flowing through this way? No current. So, as far as the common mode response is concerned, it is equivalent to simply analyzing this half. If no current flows through the resistors, the drop across them is 0. So, all that we are interested in is finding VCM, the change in the voltage here due to this character. And how much is that? It's simply the incremental change has to be small VCM. Why? Because the current source is ideal, right? You understand? Please note that RCM does not come into the picture at all, because for common mode excitations, no current is flowing through RCM. Is that clear? Okay. So, the incremental gain for common mode signals is 1, the incremental gain for differential mode signals is 0, okay, and the incremental gain here for differential mode excitation is GMR by 1 plus GMR. Is this clear? Okay. The next thing is to worry about the last man standing, which is the OpAmp. Okay. Okay. So let's assume for the purpose of discussion of the op amp, let's assume that we have made the common mode detector one way or the other, right? An example being what we just discussed. Okay. And so what is the job of the op amp? It is supposed to sense the difference or amplify the difference between the detected common mode voltage and the reference common mode, correct? So what is the based on your prior experience, what is the best candidate to do this now? Use a differential pair. I just call this to I1. Okay. What do you do with this now? On this side there must be the VCM ref. Okay. This, mind you, is the detected common mode voltage, VCM out. All right. What do I do now? Next. Okay. So what is this incremental current and what is this incremental current? People is okay. How do I proceed? I mean, come on, you had a basic course, you've done all this in gory detail before. That's not the question I'm asking. What am I trying to do here? What am I trying to do? Amplify the difference between these two. Okay. So I mean, using the differential pair, I know that the current in one arm is I1 plus some GM times the differential voltage. Another one is I1 minus the differential voltage. I want to generate a single ended voltage. Please note that the output of this op amp is only one, is referred to ground, correct? So I need to generate a single ended voltage which is some large number times the difference between these two voltages. So what should I do? Yes, Sailaditya Day, what do you think we should do? This difference in current has to be converted somehow into a voltage, correct? And what do we do? To get as large a gain as possible, you could, I mean, you would want to use as large a resistor as possible. Using a large resistor is not a smart idea, correct? So you could instead use a active load. And what do you think that active load might look like? Okay. Why have I put the current, I mean, the mirror here and not the other way around? Or which is the output of the desired output of the amplifier? BTech students, left or right? Right. Why? Dinesh Jayaraman, why did you say right? Anmol, what do you think? What is the incremental voltage at this node? No, you guys said right, right? Why did you say it? That's all I'm trying to find out. Pardon? Okay, so how about this then? Now where would I take the output? Yes, Shravan, where do you think we should take the output? Okay, the suggestion is that I should get back to my old circuit and make this as the output. Can you tell me why? Yes? Okay, so the incremental current here is Gm times V d1, right, where Vd1 is rather Vd1 by 2, where Vd1 is the difference between Vcm out and correct, and this current will be Gm times Vd1 by 2. Both these will go out and create in principle a very large voltage gain because the impedance of that node is infinite. Okay, and why do I choose this? I mean, I could have in principle also done the same thing by flipping the mirror, right, to the and then taking the left output. What is the problem with that? The gain will be wrong sign, so the feedback loop will become a positive feedback loop. Okay, so now what am I supposed to do? Yes, what do I do going forward? I connect this to right. Does it make sense? All right. So let's just quickly understand the negative feedback loop operation. If this goes up for some reason, then what happens to this character? Goes up by the same amount. If this goes up, what happens to this voltage? This must go up. Okay, and why was this going up in the first place? The current to the PMOS has increased. Okay, in which case what the feedback loop is doing is to increase that voltage, which is crushing the source gate voltage of the PMOS devices, thereby reducing the current, thereby bringing the voltage back to VCM rack. Does it make sense? Okay. So okay, and this is VDD. All right. This is the simplest thing you can do for the error amplifier. Correct? You need a differential pair to convert the voltage into a current. You need some kind of load network to convert the current, which is dependent only on the difference between these two voltages, back into a voltage. We could have used a resistor, but a resistor will be more will have lot less gain. So, this seems like one of the simplest things that one could do. Okay. And please note that, you know, as we discussed earlier, the transconductor is always in a GMC filter. The transconductor is never operating open loop. First of all, one thing there is the integrating capacitors at the outputs of the transconductor, correct? And why am I suddenly bringing in these capacitors now? Right? I mean, the next thing we'd like to do is understand the stability of this common mode feedback loop. Okay. So, we need to bring in not only all the intentional capacitors that we put in, but also a whole bunch of parasitic capacitances that occur when due to device parasitics, right. We know that the transistor, the MOS transistor has got input and output capacitances and so on. So, all these things affect the phase margin and stability and so on, right. So, when we are dealing with stability, we better put down all the capacitors that we are likely to encounter during operation, correct. The first thing is, of course, the intentional capacitance that you put to to perform the integration operation. The integration operation is happening only for the differential mode half circuit. Okay. The job of this common mode feedback loop, again I reiterate, is to keep this voltage fixed irrespective of differential mode operation, and it is going to keep it fixed to a value such that the output common mode voltage is exactly equal to VCM ref, which is equivalent to saying that when Vd is 0, the sum of the PMOS current sources must be equal to 2I naught. Is that clear? So, in the next class we will worry about the stability and what one might do to, how one might choose different parameters in the common mode feedback loop to make the common mode feedback loop stable. Okay. All right.